Hi, welcome to the channel. I'm Mrs. R. Let's do some math. Today we're talking about continuous relations. Now we've already talked about discrete relations in a different video, so if you haven't checked out that one, please go look. We talk more about what a relation is in that introduction to the word functions. When you're talking about continuous relations in your algebra class, really you're looking at some continuous graphs of things. It's not just points anymore or lists. It's a full graph where all the points connect, and you'll be trying to determine if it's a function or not. So just to remind you, a function is a relation in which each input maps to exactly one output. Now, how does this apply to graphs? So we worked in our discrete relations video with the x and y points and how those we could determine whether it was input, whether it was a function or not, based on the input going to exactly one output. And we do the same thing in the graphs. So x is always your input, remember, making y your output. And anywhere that you see the actual graph graphed, anywhere you see that blue line in this case, or your graph, your actual plotted thing, usually there's an equation that goes with it. Anytime you see it, that's where that graph exists. So there is an input there, there is an output there. For example, right here, there's a point there. It's the point 1, 0. The input is 1, the output is 0. If we look at that input and all the other possible outputs, we don't cross that line ever again. Anytime we're on the positive 1x, the only y value that matches, that overlaps with our actual plotted graph, is that one single point. So that one is good. Now we could check this for all of our grid points, right? Like I could put a dot for the grid. I can check, is there anything else on that y? Anything else as we go up or down? No. So that one's fine. The trouble with that idea is that we're still thinking discretely. I'm still thinking individual points. But remember, these continuous functions, once you graph a line, this is going to include all those tiny little points that are even smaller than the pixels. All those tiny little points that connect those two, I'd have to check each and every single one of those. But you can never check each and every single one of those because there's an infinite number of them. So we have a different strategy. Rather than checking every single input to make sure it only has one output, we're going to use something called the vertical line test. And you can kind of see maybe where this is going because I've already drawn some vertical lines on my graph. So here's how the vertical line test works. You imagine taking this vertical line that represents all the possible y's that could potentially come from the input that you're looking at. All the potential outputs that could come from an input. That's what our vertical line is. We know what the x value is. In my drawing, it's positive 1. And I'm looking at, okay, where could we have y values? As you imagine dragging this vertical line left and right to see how it overlaps with the actual plotted graph, as long as your graph only ever intersects your line once anywhere you put it, like here, my x is 0, it only crosses one time. It crosses at positive 1. And here, my x is about negative 2.5, and it's crossing at about 3.5. So as long as it's only crossing once, that means any input only has one output, and this would be a function. So I'm going to label this first graph as function. So we take that idea to any of these graphs that we're trying to determine, hey, is this a function or not? So let's come to the second graph. Imagine a vertical line, right? That's the idea, vertical line test, or matching a vertical line. And I'm going to try dragging this and see what happens. So this relation doesn't even exist over here. So I don't really care what's happening over on the very far left of this graph. Once we hit -5, it starts to exist. Now, right at -5, it's kind of hard to tell, but I think -5 is still fine. I think it's just -5, 0. But as we move in, look what happens. I'm going to use -2 input as our example. -2 as an input, we could look up to the positive direction and we see a point there that's almost at 3. But we could also look down and we see an output point that is almost at -3. So there are 2 points that use -2 as their x value. It's not quite 3, but it's really close. But you see the 2 points that I don't even have to keep going. That automatically is going to tell me that this is not a function. As soon as you find a spot where one vertical line crosses your plotted graph in 2 places or more, that means it's not a function because that input that's represented on your vertical line has multiple outputs. So I have just a couple more graphs to look at. These are not graphs that you would see all the time. They're kind of strange, but we're going to test out that vertical line to see if these are functions. Here's my vertical line. It doesn't exist here. Here's where it starts to exist. We're a function so far. And going. So far, we're just following up. It's called a local maximum where you get that peak. Then it comes back down. But we're still only ever having the blue and the green cross once. Even right here, our point where we're intersecting is 1,6. And then it starts to drop. There's no overlap yet. It's dropping steeply, but there's no overlap. Then we hit 2, -6, stay at -6 for a little while, and then come back up. So there's a lot of variation in this graph, a lot of change, some sharp peaks, but there's never any overlap with my vertical line. No matter what x value I give you, if I ask for the y value that relates to it, there would be exactly one answer. So this one is a function. Now let's check this one. So we have our vertical line. We're going to see. Okay, so far still a function, still a function, still a function, still a function, still a function. But look what happens when we get to x equaling 1. So you see, there's obviously, as you're following the function from left to right, or the relation from left to right, the first point we see as we're kind of driving along this path is 1,5. But also on this graph, on this plot, there's 1,4.5 and 1,4, 3.5, 3. All of these are points with a 1 and then something. Now there are more than I'm writing, but even just having 2 disqualifies it from being a function. So this one, anytime you have a vertical line actually in your graph, that's going to make it not a function. So you can have vertical lines that turn it into not a function. You can have just some overlapping points, like we did in our first example here, that make it not a function. Either way, if your vertical line that you're testing crosses the plotted graph in more than one spot, if there are more than one point that you could write with that same x coordinate, then it's not a function. So thank you for joining me for our talk about continuous relations and determining whether or not they're functions. This is Mrs. Robertson. I've been doing math here. If you liked the video, please actually like it on the page. That helps us reach more people. If you have any other questions, leave me a comment. Otherwise, I'll see you next time.